Hello, this is Mr. McGovern. We're looking at the fifth video in the capacitor series, and this is following on from the last one. We looked at some graphs of charging and discharging capacitor. We're now going to do some calculations with these graphs. So look at the graphs, what influences them, the formula, and do some calculations. Plus a little extension at the end, extra for experts. So these are the graphs we looked at last time, and I would suggest that you should be confident in being able to know which graph goes with which. You can see all of them are exponential decay except for one here, which is the voltage over the capacitor, which grows during the charging time. Alright, so what influence how quickly or slowly this charging and discharging takes place? And what I mean by, we've got a graph here of it discharging. If it was to discharge quicker, or even charge quicker, the current through the circuit might look like this, a sharper thing. So what are the factors that influence how quickly or how slowly we can make this graph look? So I've got my little simulation here, and you see I can charge, and we've got a charging here, and then I can discharge, and we can see the lights coming out there and the charge going off the capacitor. So I can grab from the side here a current and look at these graphs, and so we can actually look at how quickly this happens. So I'll go through the charging phase, and you can see if I sort of pause it, it's about 2 units of time on this graph here, 2 units of time to charge this. And so what I'll do is I'll discharge it now, and 2 units of time again. Same to charge and discharge. So what we'll do is on the light bulb, if I double click this, I can change the resistance of the light bulb. So I'm going to increase that resistance, make it about double, doesn't have to be perfectly double, and then see what happens with the charging time. So you can see it doesn't have as much current, but it takes a lot longer to charge. And if I just zoom in on it there, you can see it takes 1, 2, 3, over 4 units of time to charge up. So it took longer. We're not too worried about what the peak current was for now, but just the fact that it took longer. And in that same light bulb, to discharge it, you can see even though I'm zoomed in, it takes 1, 2, 3, over 4, maybe even 5 units of time. So increasing that resistance can increase the time it takes. So I'll put that back to where it was. So it was back at about 10. Cool. And then I'll look at the capacitor. So I can double click on the capacitor and I can change the capacitance. So I'll make it a better capacitor, it can store more charge. And to do that, when I change it, you notice that the plates moved closer together. So I charge up now, and you can see that if I pause again, this is taking 1, 2, 3, 4 units of time. Okay, so increasing the capacitor looks like it increases that time as well, and that should be the same if I discharge that. It takes the 4 units of time. 1, 2, 3, 4. So it looks like it's pretty obvious that in the simulation, this shows us that the larger resistor, which is my light bulb in this, takes a longer time, and larger capacitor takes a longer time. So you can put them together into this formula here. This symbol, Greek symbol tau, is our time constant for charging or discharging a capacitor, and it's just equal to the resistance in the circuit times the capacitor. Exactly what we found. How does that fit into this whole thing? So the way it works is we need to know what the peak current is, and there's different ways of getting that. And what happens is, after this time that we calculate, 37% of the max current is flowing after that time. Now, we'll tell you where 37% comes from at the end of the video, a bit of an extra for experts, but it's a number you have to remember. So you have to remember, if I've been given the peak current, say it was 2 amps, you have to be able to calculate 37% of that, and where that is on the graph, that's one of these time constants. Okay, and this keeps going. So after one time constant, after another time constant, we're at 37% of that value. So you can see I've done that in brackets by saying 37% of the last value. And I could keep going 3 times, 4 times, 5 times, right? So when we're charging a capacitor, and this graph looks different, instead of it decaying, it gets to an asymptote here and goes to max. We go through a similar thing, but not quite the same. So instead of saying we go down to 37% left, we go up 63 from 0, and you should be able to do the math that 100 minus 37 is 63, so that's where that 63 comes from. And then 63 of that remaining, so you have to look at the difference between where you were and where you're going and say what's 63% of that, and that's after 2 time constants. Okay, so it's always using these time constants, and this 37%, or in this case where the graph grows, you're going to 63% of the max, and then you can do 3 and 4 and 5. Now, the time to the full charge is how many time constants, because this is an asymptote, and it keeps getting closer and closer, but it never really gets there. You can say the whole thing's charged up in about 5 time constants, okay? So 5 time constants, 5 tau, after 5 time constants, it's 37% to 37% to 37%, 37%, which equals 0.7%, which is 99.3%. It's 99% complete after 5 time constants. So it's something else you have to remember, that you can consider the charging done after that amount of time. So, charging and discharging is influenced by R and C, and that gives that formula, time constant equals RC, and that time is also the time on the graph to get to 37%, or in the case of that graph growing, it's 63%, which is 100 minus 37. We're going to do an example of this in the next video, but the other thing you need to remember is that charging is considered complete in 5 time constants. So this is the extension. You don't need to know this, but those of you going to scholarship might want to know, where did I just pull 37 out of a hat? Where did it come from? So this graph is exponential decay, and so we can write a formula for that, is that the current at any time, which is any time I want to work out on this graph, is equal to the initial current times this exponential decay term. Now it's decay, it's got a negative, time is a value you can change, and then divided by the time constant, right? So after 1 time constant, we know that time is the time constant. That's how much time's gone on, right? So if you put that in the formula, you've got time constant over time constant, but time over time is, well, anything over anything is 1. So you can substitute that in, and you get exponential to the -1, or e to the -1. If you work out e to the -1 on your calculator, it gives you 0.37. So that's where that number comes from. All right, I'll catch you on the next video.